Okay, so we're going to start a new lecture topic now, and this is a chapter where we're going to ask a really basic question about physical chemical processes, and this is the question of why do they even happen at all, and can we predict something's going to happen or not? That's really the main question here, and how do we know whether a process is spontaneous or not? Before we go further, I want to explain what I mean by the word spontaneous. So, spontaneous process is one that occurs naturally under certain condition without any continuous input of energy. So a good example of this, like this picture is showing, if I put a drop of ink or food coloring in a cup of water, what you'll see is that that ink will slowly spread around the entire water, and eventually this entire water will have blue color, just like the color of the food coloring. That process we would call spontaneous. What is not spontaneous is the opposite process, where if you, for example, have a cup that is completely blue with food coloring, it's not going to ever be that you will see this food coloring all of a sudden just stay in one corner of that cup. What you will always see is this picture right here. You will never see this picture. So in other words, going from here to here is spontaneous. Going from here to here is not spontaneous. Okay. Now, what are some other examples of spontaneous process? I've listed a few here. When a gas expands, it always expands from high pressure to low pressure. So when you have wind, it's coming from a high pressure area where there's a lot of gas particles moving to a low pressure area. Heat transfer, that's the one that's really easy to see. It always goes from a hot object to a cold one. So if you have a hot cup of beverage, like a coffee or tea, for example, and you take it into a room that is colder, your drink will eventually become colder and will match the temperature of the room. It never is that the drink gets hotter and hotter and hotter as you stay longer and longer in that room, right? So the flow of heat is always going from higher temperature object to lower temperature object, okay? We have a couple other examples here. Table salt will spontaneously dissolve in water. Rust will form when you expose iron to air. The reason why this is important is because, of course, we want to know what is the natural direction of a particular process. If we know, then we can make prediction of whether something will happen or not. Now, the fact that there's a very specific direction for each type of process tells us that there must be some kind of a natural law that's governing how processes happen. And so we want to figure out in this chapter what that natural law is, and if we can use it to help predict the directions of chemical reaction. Now, spontaneous and instantaneous are not the same thing. Spontaneous just means whether something will happen or not. Instantaneous means whether something will happen quickly or not. Okay, spontaneous has to do with just the likelihood of it happening, whereas instantaneous has to do with the rate of how that process happened. This particular plot shows you an example of the difference between these two words. Here we have radioactive decay of two radioisotopes. So the top isotope here, uranium-238, the bottom one is technetium-99. And you can see that what I'm measuring here is the amount of isotope that I start with as a function of time. And as you can see with this Tc isotope, it decays very quickly. So in about 2-3 days, it's already close to zero. Whereas with the uranium isotope, it barely moves at all over that 7-day period. So both of these are spontaneous processes because the radioisotope both decay on its own without any input of energy. But the process of decay for the uranium is very slow, whereas for the technetium is very fast. Another example of this is just kind of visualizing this tennis ball. When the ball is being held by a hand over the floor, the ball is not going to fall. Why? Because the hand is there preventing it from falling. But if the hand is removed, the ball will spontaneously fall. So the ball, when it's held by the hand here, does it not want to fall? It still does, right? So in other words, you can say the desire of the ball to fall to the ground is the same whether it's being held by the hand or when it's let go by the hand. It's just that the hand is preventing it from happening quickly. So if you let go of the hand, which is a barrier, in this case we call a kinetic barrier, the ball will fall with that same desire as is when it's being held by the hand, okay? So keep that in mind about the different spontaneity and rate of reaction. In this chapter, we're going to learn about thermodynamics, and thermodynamics is what tells us whether something is spontaneous or not. Kinetics, which we learned a few chapters ago, is what tells us whether something's going to happen quickly or not. So kinetics has to do with rate, thermodynamics has to do with spontaneity. Now, what makes something spontaneous and not spontaneous? What we can do is look at mechanical processes and see if there's something there that will help inform us on what quantity will be relevant in chemical reaction. If you have a ball like here, and it falls to the ground, there's an energy quantity that you can calculate, and that's called the gravitational potential energy. And you might remember this if you're taken physics before, that that quantity is equal to mass times gravity times the height of the object. So when the object is at ground level, the height is equal to zero, so the gravitational potential energy is also zero. When the height is greater than zero, then you have a gravitational potential energy that is greater than zero. So for a ball that's moving from a higher position to the ground, you can calculate your delta of gravitational potential energy, which is the final potential energy, which is zero, minus the initial potential energy, which is not zero, right? This is a number that is positive. And so in the end, you get a negative number, right? So zero minus a positive number is a negative. So you're going to get your delta GPE, or delta of the gravitational potential energy, being negative. And that tells you that the process is spontaneous. This actually applies for all objects that are being dropped, right? Anytime you get your delta GPE being negative, that tells you that the process is spontaneous. So what we're trying to do in this chapter is really find a similar quantity, but for chemical reaction. So instead of gravitational potential energy, we're trying to find something called chemical potential energy. Is there a potential energy for chemical reactions that, when we calculate it the same way as we calculate this delta GPE, when it gives us a negative number, it tells us that that reaction is going to be spontaneous. Whereas if it gives us a positive number, then that reaction is not going to be spontaneous. So imagine that you have your ball here, you have it initially at the bottom, and you want it to go to this top position. So this is your initial and this is your final. Well, think about the delta GPE that you will have, right? The final position is some positive number, okay? And then the initial position is zero because you're at ground. So then the delta GPE in this case is positive. So that tells you immediately that when the delta GPE is positive, then this mechanical process is not spontaneous. So the same way later on when we look at our chemical potential energy, we want that number also when it's positive to tell us that that chemical reaction is not going to be spontaneous. Before we can find what that quantity is, we need to look back a little bit to Gen Chem 1 or Chem 11 to remember some of the terms that we learned from thermochemistry, because thermochemistry is a branch of thermodynamics. And so we want to know what some of the definitions and quantities that we already learned there. The first concept I want to remind you of is the concept of a system. So remember that in thermodynamics, the part of the universe that we're interested in is called a system. In thermodynamics, there's three different types of system: open, closed, and isolated system. They're shown right here in this picture. So an open system is a system where you can have heat transfer, and you can also have mass transfer or matter transfer. So in other words, things can go in and out. In an open test tube like this, you can imagine that air can go in and out. If you generate gas in the reaction, the gas can escape and go mix with the air in the atmosphere. Heat can go in and out through the glass in the test tube. And so nothing is prevented from happening. A closed system is where only the heat can go in and out, but then now the matter can't go in or out anymore because the test tube is being closed. And then lastly, you can have isolated system where the test tube is insulated, so heat is constant. You can't go in or out. It's just the same amount of heat that whatever you have in here, and matter can't go in or out because the test tube is closed. Okay. Most of the time in real life application, what we will have is either a closed system or an open system like this. Closed system is very often the type that we're observing, so things that occur and achieve equilibrium happens in closed system, because otherwise if things can go in and out, then the quantity is never fixed, and so you will never achieve equilibrium. Isolated system is usually only useful when we're talking about theoretical scenarios where we're trying to derive equations or analyze something in a simpler way, because by preventing heat and matter from exchanging between systems and surroundings, then I can analyze the system in a cleaner way. Now, the other term that you will need to know is surroundings. I just mentioned that previously. Surroundings is basically anything that can exchange heat and matter with the system, okay? And again, typically we're interested in closed systems, so it's really just whatever's around that can exchange heat with the system. So surroundings can be very, very broad or can be very, very limited. In chemical reaction, all we want to know for our system is just the reactants and the product particles, and then the surrounding is just whatever surrounds the reactants and particles. Sometimes it's the test that's holding the reactants and products. Sometimes it's the water that's surrounding the reactants and products because the water is a solvent and the reactants and products are aqueous solutions that need to collide with each other for the reaction to happen. The universe just is the systems plus the surrounding. So whatever we're looking at that is having that energy interchange. I want to quickly remind you of the first law of thermodynamics, which tells us that energy is conserved. Later on, when we learn that matter and energy are interchangeable, we can say that matter and energy are conserved in the universe. The way we write that is the following. So if the energy of the universe is constant, right, because conserved just means that it doesn't change, then the delta E of the universe must be zero, right? So the change in the energy of the universe is zero. There's no change because the amount of energy in the universe is always constant. And so since the universe is made up by systems and surroundings, we can say that delta E of the universe is equal to delta E of system plus delta E of surrounding, and that's equal to zero. So therefore, delta E of the system is the negative of delta E of the surrounding. This is an important point to emphasize here because what this is saying is that whatever energy flow that happens in the system, the opposite happens in the surrounding, and the opposite is signified by the negative symbol. So if you recall in Chem 11 when we talk about this, positive energy is flowing in, negative means energy out, right? So just keep that in mind. When we write these negative and positive in thermodynamics, they have special meaning. The other thing I want to remind you of is that we had discussed in Chem 11 that energy can only be transferred using two methods: heat, which has the symbol Q, and work, which has the symbol W. As a result, we can write that delta E, which is the change of internal energy of a system, is just going to go through these two processes, either through heat or through work. In Chem 11, we focus a lot more on the heat component of the equation, and specifically, we measure something called delta H, or change in enthalpy, which is just the heat that transfers in processes that occur under constant pressure. So remember that we can measure delta H using a technique called calorimetry. The delta H is obtained by any one of these three equations, but the one that you're most familiar with is probably that one right there. It's MCS times delta T, and using that you get your delta H, and that delta H represents the heat that is being either absorbed or released by that reaction under constant pressure. More importantly, though, that experimental value of delta H actually correlates with the microscopic system that we have, which is the systems of molecules, of reactants and products. Specifically, the delta H that we measure corresponds to the difference in the bond strengths of the products and the react. So when we say that a reaction is exothermic, which is delta H less than zero, we're saying that the product bonds are lower in energy, which is another way of saying that it's more stable than the reactant bonds. So you remember that we had drawn these energy diagram before, where we have reactant, we have products, and then we have a transition state where the reactants have to overcome in order to get the product. The delta H, remember, is this value right here. It's the difference between the product and the react. So if you have a picture like this, which is for an exothermic reaction, that tells you that the product has more stable bonds, therefore the bonds are lower compared to the reactant. If you have endothermic reaction, in this case, the opposite happens. The product bonds are higher in energy, they're less stable than the reactant bonds. So the drawing for that would look something like this. You have reactants lower, products higher, and still have your transition state in the middle. But then now that delta H, this quantity is going to be positive. Okay. There's one terminology you want to keep in mind from Chem 11, which is a term called state function. So state function is a function where you can find its value by just taking the final number minus the initial. It doesn't matter how you get from begin end. Okay, I don't want to spend too much time talking about it here because it was discussed in Chem 11, but it's an important idea because the quantity that we're looking for in this chapter that would help us predict whether a reaction is going to be spontaneous or not is also a state function. So therefore, it allows us to calculate its value by just taking its final number minus initial number. The last thing to remember is that there are three different ways to calculate delta H. You can calculate delta H using a method called Hess's law, where you're rearranging some reaction and adding them together to give you a target reaction. You can calculate delta H using what we call enthalpy of formation. This is a tabulated set of thermodynamic data. And lastly, we can use bond enthalpy values because remember that delta H is a measure of stability of reactant and product bonds. I'm not going to review these methods of calculation, but you should, because later on when we do some calculation with the quantities that we're going to learn in Chem 12, some of these methods, particularly Hess's law and formation enthalpy calculation method, is going to be applied again to those quantities that were learned in this class. So it's important that you remember how to do them